So this will be the electrical force plus the magnetic force to be, well, and I want the acceleration to be 0, right? So this tells me that I want the magnetic force to be the negative of the electrical force. The negative means opposite direction. If one of them is up, the other force has to be down so that they add up to 0, as long as their magnitudes are the same. So the minus sign means opposite directions. But I still need for the forces to add up to 0 for their magnitudes to be the same. So what is the magnitude of the magnetic force in this problem? It's going to be the magnitude of the charge, which is E, times the magnitude of the velocity vector, which is the speed, V, times the magnitude of the magnetic field, right, which is B external, times the sine of the angle between the velocity vector and the magnetic field. Now, which way is the velocity vector pointing? To the right. Which way did we say the magnetic field is pointing? Into. So what is the angle between the velocity vector to the right and the magnetic field into? 90 degrees. And what is the magnitude of the electrical force? It will be the magnitude of the charge, which is E, times the magnitude of the electric field, which is E external. So notice that the charge of the electron cancels. Sine of 90 degrees is 1. So the electrons, if they move at this speed, if I tweak the electric and the magnetic field, the charged particles are going to go through. And by the way, notice that this result is independent of the charge. The charge canceled out, right? So this would be any charged particle. Any charged particle, right? Because the charge is going to end up canceling, right? If they move in this crossed electrical magnetic field region, with the electrical magnetic fields cross in the correct directions, appropriate directions, the charged particles can go straight through, undeflected by both the electrical and magnetic field. There will be individual electrical and magnetic forces, but together they'll add up to 0, and the charged particles are just going to go straight through. What if, so this here is called a velocity selector. It is called a velocity selector because what happens if you have a whole bunch of charged particles coming in here? Q1, Q2, Q3, V1, V2, V3. What if you have a stream of charged particles coming in? Well, those particles that have this speed equal to the ratio of the electric to the magnetic field are the ones that are going to go undeflected. So for example, if the magnetic field is weak, small, let's say this magnetic field is weak for the charged particle, then the magnetic force, which is down, is not going to be as big as the electric force, that the charged particles are going to go up. If the magnetic field is strong, right, then what will happen is that the magnetic force due to the strong magnetic field will be big, and if it's bigger than the electrical force, then the charged particles are going to go down. And if the magnitude of the magnetic field vector and the electric field vector are such that the ratio is equal to the speed of these particles, they're going to go straight through. So this unit with this external and external electrical magnetic fields will select from this string of particles only those particles for which the speed is this. All the other ones, if the speed of the particles, if it's too big, the magnetic force is too big, they're going to go down. If they're moving in too slowly, then they're going to go up. So it's called a velocity selector. And what's cool about this is that, what if you put like a wall over here, like an obstacle, and there's a little hole over there, so that these charged particles, Q, mass M, right, make it through that hole. So can I write this over here? I'll just write this here. Can I erase this? So what happens if in this region, if they come in with the correct speed and with the right speed, they'll go through the hole, and in this region there is only a magnetic field pointing in the same direction. Let me give it a slightly different value. So this is a uniform magnetic field region. Let me call it, into the board. Let me call it B external prime. Usually it's the same magnetic field as this one, but I want you to differentiate the two of them. So when this charged particle, in this particular case, if these are electrons, for example, when they enter here, they're negatively charged particles, in which direction will those electrons be deflected? Or, let's just say they're negatively charged particles. They don't even have to be electrons. They could just be. Once they enter the magnetic field region, there's only a magnetic force. And which way is the magnetic force going to be?
Down.
Down, right? Magnetic force is going to be down. So the magnetic force will be down. Perpendicular to the velocity vector, right? Does that mean that the charged particles will speed up or slow down? Speed up or slow down? What happens when the velocity vector, well, if the force is downwards, the acceleration has to be downwards, right? Because F equals ma. I don't care if this is a positive or negative charge. The mass has to be positive, right? So the mass is positive, so the acceleration will be down. So what happens when the acceleration vector points perpendicularly to the velocity vector? Will the particles speed up or slow down? Stay the same. But there is an acceleration. So what's going to happen is that they're going to change, the velocity is going to change in direction, not in magnitude. And because it is perpendicular, the acceleration vector is perpendicular to the velocity vector. This is called centripetal acceleration. This is 185. So what will happen is that this charged particle is going to bend. What happens when it is here? The velocity is going to be pointing this way, but the acceleration vector and the magnetic force will be pointing this way, perpendicular to it. So it'll keep bending. When it's here, it'll be like that. And, I'm supposed to have this all over the place. The end result is that this thing is going to go like this, and boom, it's going to hit over here. And when it hits the wall over here, ding, it'll make up a little bit of light. I don't know, it'll hit something that's, coated with phosphorus, and it'll emit some light. So you know where the hole is, you know where it hit, because, there's a little light produced. So you can figure out this diameter of this circular path. And half of the diameter, right, that would be the radius, right? Let's say from here going this way, from here going that way, that's R. That's the radius. So maybe I shouldn't call it capital R. You might think of that as resistance. I'll just call it little r. And this is the diameter. So from the middle of the hole to where it hits the screen, you just measure that with a ruler, whatever. Half of that is the radius, so this thing is in circular motion. This is in uniform circular motion. This is chapter 5. And then you can do this. The sum of the centripetal component of the forces is equal to the mass times the centripetal component of acceleration. There's only one force acting on this thing. It's the magnetic force, and it happens to be pointing towards the center of the circle. It doesn't get easier than that. So, and that force is the magnetic force, because there's only a magnetic field over here. There's no electric field here. So, the component of the magnetic force along the centripetal axis is just the magnitude of the magnetic force. There's no sine and cosines, and that's it. That equals m. And the component and the centripetal acceleration. Anyone remember the formula for the centripetal acceleration? V squared over r. And then this one will be like, the magnitude of that. Let me write it as q v b external prime. Now it's moving in this magnetic field. And what is the angle between the magnetic field vector and the velocity vector throughout this motion? Magnetic field is into the port and the velocity vector is on the port, right? So they're always at 90 degrees. So that's the magnitude of a magnetic force which has a cross product in it. So this is one. The speed that these particles have is the ratio of the electric field in this region to the magnetic field in that region. That's that one, right? Essentially it's that one, right? I can just put it in there. So this becomes Q. V, actually I can just cancel this with this. And that's a 1. And then that speed is E, external. And I'll put it over the other magnetic field without the prime of R. So notice that I can measure the mass divided by the charge. That would be what? It would be R times B external. I'm solving for M over Q, so it would be R. This is prime, this is unprime, so that would be B external, prime, B external, divided by the electric field. And I'm doing M over K, so that would be proportional to R also. So, if you have a stream of charged particles coming in at different speeds, and you don't know the mass, you don't know the charge of the particles, those particles that have this speed are going to move through this velocity selector undeflected. And then once they enter this region where there's only a magnetic field, there's only going to be one force acting on them in this region, the magnetic force, which, by the way, remember that this vector has to be perpendicular to this and this, right? So because this vector is perpendicular to the velocity vector, it's going to give it a centripetal acceleration. And all that's going to happen is that the particles are going to be deflected. And they're going to follow a circular path, right? And depending on where they hit, right, you can measure the diameter of that circle. Half of that is the radius. And if you know the radius, once you measure that, you control these electrical magnetic fields. You can then measure the mass to charge ratio for these unknown particles. So in a mass spectrometer, there's a velocity selector, and then there's another region like that to identify the particles coming in, or to be able to measure their mass to charge, or charge to mass, either one, right? You can just invert that. So this is just an application of what happens when a charged particle is made to go through origin of crossed electrical and magnetic fields. And if you adjust the values of the electrical and magnetic fields and adjust it so that the speed of the particles is equal to this ratio of E to B, they're just going to go undeflected, and then you select those particles that have the right speed, and then by having them move in the circular path in this magnetic field region only, you can then measure where they hit. So you can measure the diameter of the circular path, half of that is the radius, and then you'll know what the mass divided by that charge is for those unknown particles. It's just an application. And I think I have some of those notes in chapter 27. These are applications. So that's the torque, magnetic potential energy. This is what I talked about a while back ago. Well, today, right? Earlier today. Origin of a charged particle. In this picture here, there's an external magnetic field. The X's represent a magnetic field that's directed into the page, into the board, into the screen. And if a charged particle, let's say a positively charged particle, moves to the right, it enters this region moving to the right. Well, what will be the direction of the force exerted by this external magnetic field on this charged particle? Velocity crossing to the magnetic field. So the velocity is this way and the magnetic field is this way. The force is going to be up. And since in this picture the charge is positive, then the force is going to be in that direction. That force is perpendicular to the velocity. It'll just make it go in a circular path. And it'll go around. And you can measure then the radius of it, or relate the radius, right, to the charge and to the mass and the speed. And just F equals ma for circular motion, uniform circular motion. And you end up with a formula like that. And you can talk about the period of revolution, how long it's going to take this thing to go around, because the distance around is 2 pi times the radius. The speed is v. It's a constant speed because the magnetic force. See, the magnetic force doesn't have a component in the same direction as the velocity vector, so it's not going to make it speed up. The magnetic force doesn't have a component in the opposite direction to the velocity vector, so it will not make it slow down. It can only deflect it. And so you can write down formulas for the period of revolution, how long it's going to take it to make one trip. For uniform circular motion, it's just going to go around the distance around the circle, which is the circumference, 2 pi times the radius, divided by the speed. That'll be the period. Whatever the period of revolution is, the frequency of revolution, you can talk about an angular frequency, which is 2 pi times f. So anyway, these are just applications. Pull some things from physics 185. That's what that is. And then we talked about this sort of thing. Some time ago, I said, what happens if there is a magnetic field this way? And you might remember, I took my keys and I threw them perpendicularly, and then we argued that the keys, if they were charged particles, right, moving in perpendicularly to the magnetic field, then they would go around the magnetic field lines. And then I said, what happens if I throw the keys, or if the keys are coming in at an angle? Then they'll end up spiraling around the magnetic field. So that part of it there, I talked about already. We talked about how the northern and southern lights may be produced. Here's the velocity selector. It's a different picture. Particles here are coming down instead of like in this picture that I did over here to the right. So the particles come down. There are 2 plates that are parallel, positively charged plate, negatively charged plate. The electric field that these charged particles generate is to the left. Those are the red arrows. The X's are external magnetic fields, into the board. And so, you follow the argument. That's a positive charge, and they'll just end up going straight through. In this picture here, these were not electrons, they were positively charged particles, right? So the electric field is to the left. So by this formula over here, the force on the positively charged particle will be the same direction as the electric field, which is to the left. The velocity is down this, screen. So the velocity vector is this way, and the magnetic field is into the board. velocity cross into B, magnetic field, will be that way, right? To the right. So the magnetic force is to the right. So if the magnitude of this electric force is the same as the magnitude of this magnetic force, the forces will cancel and the particles will just keep on going straight through. And then you get the same result, that the speed would have to be equal to the ratio of the electric field to the magnetic field in that region, and then they'll go undeflected, which is this. And in the mass spectrometer, you just have that extra region right here after the velocity selector, where there is just a magnetic field, and then the particles, will follow different paths as they, depending on their masses and charges, will follow different, circular paths with different radii, and then those could be used to identify the mass to charge ratio of the particles. And that's just another application. I think we talked about forces between two wires that have currents in them in the same direction, parallel wires in the same direction and opposite directions. We said that if the currents are in the same direction, they end up attracting. If the two wires have currents that are parallel and have currents that are in the opposite direction, they end up repelling. We did this problem on the board. I derived this expression. Anyway, we talked about the Earth magnetic field. So, what I would like to talk about next is, I'm going to just begin this topic here. So basically over here, I kind of said a few words about this in response to a question that was asked or comment that was made by one of you in class. I don't remember who made the comment, but I think, I don't know, it might have been Brian, but, or Roy, was it you? I think it was Roy, right, who made the comment? So the problem that I did today, there was a magnetic field pointing up, and there was a coil with current in it. Right? So this magnetic field then exerted forces on the various segments of the coils, right, that had currents in them, and the forces caused, the top to come out, the bottom to go in, and it made it spin. And we calculated the torque and so on. Now, what this chapter is about is the following. It's about having a coil with no current in it. No current in it. Initially, no current. So in other words, in these formulas, like, if you write then if this is zero, even if you have an external magnetic field, this is going to be zero. No current in it, right? In fact, that's what I have this here. So what I have here is a coil. This is just one wire. And imagine just 1, 2, 3, 4. If I remember correctly, this coil has 3,250 turns. It's probably written somewhere, but that's the number that I remember. 1, 2, imagine 3,250 turns. And then one end of the wires is connected to here. And so that would be this. That would be like a continuation of that wire. And the other end of the wire is connected here. So this is all one wire that starts over here. It goes and then comes out over here. It's just one wire, which makes up a coil with many turns, with 3,250 turns. I'll just do it like this. And, this is an open circuit. just a long wire, right? There's nothing connected here, nothing connected there, right? No connection, no connection. And what I'm going to do is this. I'm going to extend this end of the wire to here. So that now the wire goes like, comes out over here, but then it continues here. It goes through this unit, comes out over here, and now I'm going to close the loop. So now I have a loop, a coil. Well, a closed, right? Now I have a circuit. Maybe that's better, a circuit. But I don't have a battery. All this thing does is just an extension of this wire over here. And this thing has a needle there. If the needle reads 0, then there's no current anywhere. There's no current. The current is 0. So right now, that's supposed to be reading 0. There's no current. Well, there's no battery. This is not a battery. All this does is measure the current in this circuit if there is a current in it. So if I take, I don't know, some power supply and I connect and I create a current, and this needle will move, right? So no batteries, no power supplies. How can I create a current in this coil without even touching it? I don't want to connect the battery, I don't want to connect the power supply. DC power supply, AC, I don't want to connect any of that to it. How can I get a current going in there? So previously we had a magnetic field and we had a coil with current in it, right? There was a coil with current and a magnetic field. What we have here is a coil, but there's no magnetic field because there's no current.
Could you introduce a force?
So it turns out that if I bring in a magnet, which produces a magnetic field, so now I have a magnet and a coil, but the coil doesn't have current in it. If I put the magnet and I just hold it there, this coil is in a magnetic field, the magnetic field of the magnet. But there's no current in the coil. There's no current in it. In fact, let me do this. I put a magnet. There is a magnetic field going through that coil. But this thing is saying, no, there's no current. And remember that when there was no magnetic field, the needle was also saying that. Okay. So, how can I, in the previous case, we had a magnetic field and we had a current in a loop, right? And then by placing this coil with current in it, in this magnetic field, the magnetic field made it spin. I got motion, I got kinetic energy, rotational kinetic energy out of the current in here, and the magnetic field produced, magnetic field here, right? Here I have a magnet which creates a magnetic field, but there's no current, and there's no motion. Well, it turns out that if I change the amount of magnetic field that goes through this, if I change, I don't care if I make it big or small, as long as it's changing, while that amount of magnetic field through this coil is changing, there will be a current produced. So if I want to make a current, all I need to do is pull the magnet out. Because right now there is a magnetic field through the coil. If I pull it out, the magnetic field is going to be 0. As I was pulling it out, the magnetic field was changing. The amount of it through the coil was changing. And during that process, there is a current in the coil. See? Pulled it out and there was a current. Now I leave it over here. Oh, it's okay. Now I'm gonna put it in, and watch the deflection. It's gonna be the other way. If I put it in the same way, it goes the other way. So you want to make electricity, just change the amount of magnetic field going through this thing. There is an electricity, there is an electric current in this coil. And the needle is showing it. Notice, when I put it one way, the current is one way. When I put it the other way, the current is the other way. Like left, right, left, right, left, right, left, right, left, right, left, right, left, right. The electrons are going crazy. They're like, oh, which way? Come on, make up your mind. We go this way, then 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 we go. Yes, come on, keep moving. That's it.
That's AC, right?
And this is AC because the current is changing direction. If so when the needle deflects to the left, it's like the current in this coil might be this way. And when the needle deflects to the right, now the current is the other way. So the current is alternating in direction. That's what AC stands for. AC stands for alternating current. What about the current alternates? It's the direction of the current that alternates. Okay? So it is actually simple to make electricity. What you need is a magnet, a source of magnetic field. You need a coil, and you need to change the amount of magnetic field through the coil. Notice that I can put the coil like that, right? So see, I can put the magnet right here. Is there a deflection of the needle? So there is some magnetic field going through. Actually, this is the south, so there's a magnetic field coming in this way, through this coil. But it's not changing. Notice what happens if I bring it closer, 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 bigger, bigger, bigger. That needle must have been moving, right? And now I'm going to move it away. Away, 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 away. And then as I do that, the magnetic field is getting smaller, 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 smaller. There must have been a current over there. If I put it over here and I hold it here, nothing happens. Just as if I take it and put it there. Nothing happens. It's the change that matters. It's the change in magnetic flux. The name given to the amount of magnetic field through the coil is magnetic flux. So if I change the magnetic flux, then there is a current produced. Do you hire people to do this to make electricity? Oh, I gotta go to the restroom. And then there's a blackout in the city. Wow. And the traffic lights don't work. Boom, 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 lots of accidents and so on. I'm sleepy. I need to go get a Starbucks or something, to wake me up. I'm tired. And then there's a blackout, right? So you don't hire people to do that, right? Or are you gonna pay me more money per hour? No? Okay. And then, help rescues.
Does rotating the magnet do the same thing?
Yeah, so notice, what if I hold this and I move the magnet in and out? What matters is the relative motion.
I think you meant flipping the poles.
Yeah.
So having
It will go the other way.
Like
Of the
spinning
magnet.
Well, it'll go like that, and then as I do this, then oops. But yeah, it'll do that. Except that if I spin this and I hit over here, right?
The magnet, not the.
like if you take the magnet and your hand. There you go.
Yeah, it goes the other way. And so we are going to determine which way the current is going to be. We're going to figure out. I'm going to teach you how to figure out which way the current is going to be in the circuit. Is it going to be this way? Is it going to be that way? I mean, this coil is either going to be this way, right? Because the wire is like this, right? So the current is either going to be this way or this way. So we're going to figure that out. It's actually kind of cute how that works. It's called Lenz's law. It's really, really, really pretty. So we're going to figure out which way the current is going to be induced by the changing magnetic flux. So the magnetic flux is just the amount of magnetic field that goes through this loop. If that amount of magnetic field through the loop changes in whatever manner, if it changes, while the change is taking place, there's going to be a current produced. What we want to be able to figure out is what will be the magnitude of that current, how many amps is it going to be, and which way is the current going to be in the circuit, right? So that we can fully, so we have to figure that out, and we learned that in this chapter. So the symbol that we use to denote the amount of magnetic field that goes through the loop is this letter, capital Phi, I guess, right? It's magnetic flux. It's the name of it. But, you know, let me kind of, it's a quantity that people get confused about, but there's no reason to be confused, really. The flux is the amount of something that goes through something. You can talk about the flux of people at the door. Right? It'll be like the number of people going through the door. Right now, no one is going through the door, so there's no flux of people through the door. There could be air blowing from here, rushing out the room through the door. Then you can talk about the flux of air out, or through the door. If, there's water over here that's, running that way, we can talk about the flux of water through the door, right? Or what if it's raining outside, and I hold this loop, and suppose it's raining and it's not windy. The rain is just coming straight down. And I hold the loop like this. And the raindrops are coming in. What will the flux of rain through this loop? Nothing. No raindrop is going through the loop. And what if I put the loop like this? Then in this case, some drops are going to go through the loop. And what will be the orientation of this loop so that I get a maximum flux of rain through the loop?
Perpendicular to the raindrop.
Exactly, like this, right? So, what happens if this is a magnetic field? That's not going to work. Suppose, stay, please. Suppose there's a magnetic field in this region pointing straight up, and I put this coil or this loop like this. What will be the magnetic flux through it? Zero. What if I put the loop like this? Then I'm going to get maximum magnetic flux through it, right? So the magnetic flux depends on, well, I want to know how much magnetic field goes through the loop. See, what happens if I make the loop like, a tiny loop like this? Will the magnetic flux be a lot, even in this orientation, or a little bit?
It's maximum.
But will it be a lot or a little bit compared to this?
Much less.
Much less, the other case, right? Uniform magnetic field everywhere. So the bigger the area, the bigger the flux. The bigger the magnetic field, the bigger the flux. But the orientation matters. I can have a big area and a big magnetic field, but if it's like this, there's no flux. I don't care how big that is, and I don't care how big this is, there's no magnetic flux through this thing. So look at the definition of magnetic flux. It's the dot product. So it's the dot product between the area vector for the loop and the magnetic field that the loop is in, the external magnetic field. Like, remember what we said about the area vector a little while ago? What happens if the loop is like this? What is the direction of the area vector? Well, it's either that way or this way. And you usually figure out the direction by looking at the direction of the current. But there's no current in this loop yet. There's no current, so I can just say it's either that way or this way. It doesn't matter. So I'll just say that way. So the area vector is that way. There's no mu, there's no magnetic dipole moment. Because the magnetic dipole moment, we said, was I times A, but there's no current right now in this loop. There's no current in it. So there is an area vector, but there is no magnetic dipole moment because there is no current in the loop. Right now, this is just a ring, no current in it. Right? If I position it like this, there is a magnetic field, but there's no current in it. There is an area vector, but there is no magnetic dipole moment to this thing because it doesn't have a current in it, right? Yes? So, if I position the loop like this, then I can say that the area vector is either that way, it's gotta be perpendicular to the plane of the loop. So I can say that it is that way towards you, or this way towards me. So, if the magnetic field is up, and the area vector is this way, what is the dot product of these two vectors? Dot product. Dot product. Is the magnitude of this vector, the magnetic field, times the magnitude of the area vector times the cosine of 90 degrees. What is the cosine of 90 degrees? 0. So no flux. Yes? No flux. If I position the loop like this, so notice that mathematics of the dot product of the area vector and the magnetic field vector gives me the right result. Because if the magnetic field is up, or down, and I put the loop like this, none of the magnetic field lines are going through the loop. The magnetic flux through the loop is 0. So that mathematics works out great. And what happens if I now position the loop like this, relative to this magnetic field, which is up? So if the loop is like that, I can say that the area vector is up, perpendicular to the plane of the loop, or down. Well, I'll just choose up. Well, if the area vector is up and the magnetic field is up, what is the dot product of two parallel vectors? It's the magnitude of this times the magnitude of this times the cosine of 0. So I'm going to get maximum flux. So that's the definition of magnetic flux. It's just the dot product between the external magnetic field that the loop is in and the area vector for the loop. But because the dot product also contains the cosine of the angle between the area vector and the magnetic field, right? Then more generally, well, not more general, actually this is the more general expression, but you could also express magnetic flux as the magnitude of the magnetic field, external magnetic field, the magnitude of the area vector of the loop, and then the cosine of the angle between the loop and the external magnetic field. This term over here takes into account the orientation of the loop relative to the magnetic field. So when you were saying what happens if you rotate the loop, or you're just changing phi. And if you change phi, if you change that angle between the area vector and the magnetic field, if you change that angle, you'll be changing the magnetic flux, and there will be a current induced in the coil. It's just that, it was kind of awkward for me to show it with a big thing and a small magnet. In order for me to twist this, I had to pull and, well, anyway. But Faraday, Michael Faraday, 1831, I think is when he did this. My goodness, almost 200 years ago. He said, if this magnetic flux, if the magnetic flux, which is B dotted with the area vector, if that magnetic flux changes with time, there's going to be a voltage induced in the loop or in the coil. And what it's like by changing the amount of magnetic field through it, it's like I connected a battery to it, which drives this current in it. So this EMF is the EMF is it's a voltage induced in the coil when the magnetic flux, the B means magnetic. This is if you have one loop, or if you have a coil, then you have N turns. If the magnetic flux through the loop changes with time, there's going to be a voltage induced, which is going to drive a current. What happens if there is a magnetic flux, but it is not changing with time? Well, ddt of a constant is 0, so then there's no voltage. That's what happens. There is a magnetic flux right now, but it isn't changing with time. So then there's no voltage induced in the coil, so there's no current resulting from that. And what happens if there is just no magnetic flux through it? Well, there's no magnetic flux through it, and it's 0, 0, 0, 0, 0. So this is 0, but it is not changing with time because it stays at 0, that there's not going to be a voltage induced, and there's not going to be a current. But what happens is, if you change the amount of magnetic field going through it,
It's not moving. It's
then
not-
there will be a voltage induced.
I didn't do that.
Is it connected?
No, it's.
Uh-oh. You broke physics.
There we go. There we go. And something was loose. I mean, it's like magic, isn't it? Light. But of course, it's physics. So, what's up with the minus sign? We need to talk about the minus sign. Remember how I said I'm going to teach you which way the current is going to be? That's where the minus sign comes in.
Oh.
There's a reason for that, so we have to talk about that. And then, so we'll continue next